Okay. So welcome everybody to this morning session. Our first speaker of the day is Professor Andreianov from the University.
Thank you. Many thanks to the organizers for the invitation, and it's a big pleasure to meet colleagues again who speak in presence. I will present a talk which actually will contain two sub-talks somehow to related subjects. One which was announced here about local form factors for many practical approximations of like from Richard's model and applications, and a minor part which, if I'm quick enough, I will be able to explain about interface coupling conditions for LWR with point constraints. And both are related to the questions that were already dealt with in this conference, in particular in the talk of Yannick Holler, where it was the subject was to determine appropriate coupling conditions at interface or at the node from some considerations which are compatible with the model, with the idea of the physical process that is going on. And so I will roughly speaking present two techniques, one many particle approximation and the other one interface coupling conditions formalism for dealing with this kind of situations in the scalar context of a light with Richard's model. And these are joint works with Massimiliano Rosini here present twice, and with Graziano-Stivaleta present here as well, who has just completed his PhD in L'Aquila, and a small part with Theo Gerard, which is my PhD student in TUF. So I will speak about two problems which I first represent and then I will detail. The first one is known as the huge model for pedestrian evacuation, and I consider it's 1D version, and it is a non-regularized 1D version. So after reduction, due to the simplicity of the ideal situation, I find myself with a forward-backward LWR. Here, forward-backward is not like in Enrique Zuazo in time. It's just forward in space towards exit 2, which is in front of the corridor, and backward in space towards exit 1, which is on the other side of the corridor. And that's why you have this sign selector, which makes appear an interface psi of t, which dynamics is prescribed by an integral equation, which makes appear here the cost function. And my talk will be about the linear cost functional, which is at the same time very much limitative, and in particular, some of our techniques really use the linearity here. And at the same time, it's interesting for engineers because they can more easily play with this parameter alpha, trying to optimize in particular the evacuation time, which is the main variable, the main target in these questions. And this is a 1D, this is the most basic 1D case of the general model. Sorry. Of the general model of huge, which is here. So here you find a part which is direction field. It is given by a Natanov-Hyde equation, which features this cost. You have some boundary conditions that are different on walls and the exits. All this I will not discuss in detail. And so the main feature is that you have a moving interface which corresponds to the singularities jumps of this gradient phi, solution of the Econo equation. And in this situation, the well-positiveness results for this model are known for the case which we can call no-edged switching, which means that every pedestrian in the crowd will decide his way to the right and to the left and will never change, which is actually the very limited situation because the idea is exactly that pedestrians can change their mind if they find themselves on the other side from the interface. So this is somehow a case which does not describe the dynamics which is interesting, and still these results are not easy, and there are many people present here who worked on these questions and paved the way to more general results I will try to present. The situation is different if your phi is regularized, for instance, by adding diffusion. Then you have much more complete theories elaborated in particular by the team around Peter Markovich and Marie-Thérèse Wolfram, and more recently, Rinaldo Colombo, Maria Gocchini, and Massimiliano Rosini. So I will concentrate on the original model. And the second problem I will deal with, it is about two variants of point constraint LWR model. It's about flux constraint, which is by now a classical problem, very well solved, and velocity constraint, which was a question I was asking for several years to Paula and to Rinaldo about why in this situation where you consider LWR with an embedded interface, you don't see it from this equation, but you see it when you see the second line where something is prescribed. Either the velocity should be less than some given value v, which I would say quite a standard situation you can imagine, where you have a very long road and you have just 1 kilometer where the velocity is limited, say, to 50 kilometers per hour because there are some accident or something going on, and you would not like to model it as an extended site. You would like to treat it as a point site if you are going from one part of Europe to another, crossing several thousand kilometers. Okay, and so this is something that I understand quite well from the intuition, from the, say, like a driver, and this is what mathematics tell me. This is a nice mathematical condition on the flux limit. Okay, it is nice mathematically because this quantity flux at x equal to 0, you have a direct access to it from the distributional formulation. Roughly speaking, this flux has a weak trace, which is not the case of this velocity. So the interpretation of this is more clear, and my final goal will be to try to show you the interpretation of Z. So I will give the answer at the end of this slide, and then I'll try to assess it. So here the map T or the map V are constrained at x equal to 0, the bottleneck, and it prescribes the maximum possible value either of the velocity or the flow of the current. And the typical approach to this kind of problems is define solutions via defining Riemann solver. And for flux constraint, it was done by Colombo and Duartin in the following sense: if the bottleneck flow wants to be above the value Q, then a non-classical jump appears precisely at the saturated flux level. And from this, they derive a pure PD definition of solution with entropy inequalities and all this. They derive well-posedness by applying the wavefront tracking strategy with BV bounds. And through these adapted entropy inequalities, they characterize fully the solution, which is unique. And my question was, the question we dealt with Carlotta and Massimiliano was, what would be the Riemann solver for the velocity constraint? And then trying many things, Max once wrote to us, okay, I think I know what happens. The velocity constraint will boil down to flux constraint. More like a directly boundary condition is transformed to the Bardos-Leroux-Nedeljk interpretation of the boundary. And the question I want to treat here is how should we assess these heuristic Riemann solvers? Okay, this one looks very convincing and is just a small check that I will do on this. And this one looks less justified, and so we will be more happy to see these conclusions supported by some kind of traffic compatible and mathematically sound procedures. Okay? So here are more precisely the questions that are more or less in common in these two models. The first one, like the question Yannick dealt with in his talk, how should we interpret the model singularities? What's going on the interface? And the second one, why can we trust these models in the sense that if you trust LWR, then on the top of LWR, you add some other phenomena. Why is this consistent with what you want to model? And the answers would be, the tools in use and the ingredients would be as follows. Firstly, in the hyperbolic community, the first thing we think about is vanishing viscosity. But this is, to the best of my understanding, not traffic consistent. I see the fact that Khrushchev admissible shocks are traffic admissible as a coincidence, not more than this. And then the very natural procedure is, if we have a Riemann solver that we trust, then we do waveform tracking analysis, and at the limit we find existence and, if possible, characterization of solutions. And towards this, a typical procedure is construction of profiles, for instance, construction of traveling waves. And I will not speak about Wenshen's work on very much related problem, but it's really very much related, and it is focused on construction of profiles. Okay? Now, because I'm precisely concerned with interface problems, one thing I want to tell you is that you can exploit very strongly the analogy with what you know about the boundary conditions. So in this case, with the Bardot-Leroux-Nedelik boundary behavior, or if you speak the language of supply-demand formalism for traffic, it is very close to what I want to say. And here I take the insight from the work I developed with my former PhD student Karim Azbiki. It is generalized boundary conditions formalism, from which I derive the formalism of interface coupling conditions, which will be one of the tools I want to present towards answering these questions. And the second tool, many of you know, and there will already one talk about it, and there will be at least another one, is a kind of hydrodynamic limit from a traffic significant many particle model. Okay, there are many particle models called follow the leader, but the one which was identified is particularly close to LWR, starting from 2015 by two independent teams, one of Marco Di Francesco, Massimiliano Rosini, with former and recent PhD students, with Graziano sitting here, and the other one of Helge Holden and Nils-Henrik Risebron, from a very different from pure Lagrangian perspective. So these theories are somehow complementary, and because it's Massimiliano who put me on this topic, I'm in this side of the formalism, this side of approach. So what is known from this or that way is that the follow the leader model is a convergent approximation of FWR, and it is a little bit different from the approximations like Wenshin viscosity, waveform tracking, monotone numerical schemes, and BGK approximations that Yannick presented yesterday. It has a small problem. It is not order preserved. It is not L1 contracted. We thought it was. We spent lots of time, and then once Massimiliano came with a counterexample, which we published. So this is a little bit of a problem in the general way I'm used to deal with discontinuous flux problems. So finally, the way we prove convergence is a little bit different, less focused on the stationary states than it is the case for the previous approximations I mentioned. And I will focus on the two following ingredients for interface LWR kind problems. The additional ingredients are local compactness arguments. We really found that instead of looking for global DV bounds, which were finally unable to prove, even if we feel that they should be there, we use local compactness arguments, so weaker compactness arguments, and adapted entropy inequalities as more or less usual, since the Pertamo-Deuce work, which introduced this idea. It is more or less usual to characterize in PD terms the solution. So I will speak about formalism of interface coupling conditions if I am quick enough, and for sure I will speak about local compactness for FTA and what we can derive from it. And the points I will address precisely are for the Hughes model. The main thing, that's why I'm giving this talk essentially, is that we are able finally to prove existence for the original model for general data. For linear costs, okay, it's not complete, but already for linear costs, it was unsolved actually. Then we did it in a traffic consistent way by giving an FTL algorithm, and actually this is an accurate FTL algorithm with some fine properties that really make it a discrete Hughes model. It's not an approximation of the contiguous one. You can rather see it as a discrete Hughes model which converges to the contiguous. Then I will discuss a little bit of evacuation time versus cost parameter, because this is a question that interests people in the engineering community. And because I really like uniqueness questions, we also did a part of work about uniqueness strategy, which will essentially focus on the limitations. Somehow I will say you that what worked for uniqueness for this moving interface problems with this continuous flux does not really work, or works in a very limited context for the huge models. But this also gives you idea that if you change the part of the model which is the most subject to discussion, that is the definition of the turning curve, the way you compute the turning curve from the solution of from the crowd density, then you can hope for uniqueness. Roughly speaking, the turning curve should be more regular if you want to have uniqueness in a natural loop. Okay? Then, beyond this first existence result, once we use there is existence, and we use that rather weak compactness strategies for alone, then we looked with my master student Theo Gerard for more pure mathematical existence strategy with fixed point. And also the question is, can we do it for more general costs? With the final goal, which is, I think, quite ambitious at the present stage, to go towards multi-D versions of the huge model, possibly regularized more or less, possibly with a partial parabolic behavior in LWR. But our goal at that is to learn more about multi-D discontinuous flux problem by working on this multi-D. But it's 3 years after that, maybe we will have something like catechism. And then for the velocity constraint LWR, this is a work with, I forgot to say that this is a preprint with Rosini and Schiavalletta, and this is a published work with Rosini, which we have to continue because we only did the numerical assessment. We left tools at that time for the rigorous limit. Now, using insight from A, we have 90% of tools, and it's almost finished. And the second part is the assessment, another formalism of interface coupling conditions that derives from the formalism of boundary. So this is kind of BLM thing applied to the interface. Now I go to the Hughes model. The first shot, many particles with the focus on the convergence. So this is a technical transparency. For those who know LWR FTL approximation, just put here, you have part of particles which move forward with velocity v, and part of particles which move backward. And the distinction of the two is according to some turning curve that we call zeta n, and not psi n, which will be important. So more in detail, you give a total mass, which is capital L, the total mass of the flow. You take n particles, you set small l, which is capital L over n. You initialize with some positions such that you have a kind of minimal distance where rho maximum is the maximum allowed speed in your system. So all this usually comes from an initial datum. This can be seen as discretization of a given initial datum. But my point is, see it as given particles, which are distributed according to some minimal distance, and then launch this dynamics. This is the standard LWR. So you go with a speed which is adjusted just to the distance between the previous driver and yourself. And the previous driver, it can be a curve to the right or a curve to the left, according to which side from the curve you are situated. And then the global density is assembled from these quantities that appear here. It is just a piecewise constant in space and continuously evolving in time density. So this is something rather natural. What is less natural if you start by thinking approximation, and it is more natural if you start of thinking of discrete model, is the definition of the turning curve, which is different from the one taken by the team of Di Francesco, Fagioli, Rosini, and Giovanni Russo. It is based on exactly counting particles located on each side from side n, from zeta n, and not on the reconstructed density, which is somehow fake. So what has real existence in a corridor filled with pedestrians is counting of pedestrians. And that's exactly what Massimiliano and Graziano proposed to do. Well, now we should say that the well-positiveness for this stuff is delicate because what we have is a non-linear ODE system with right-hand side, which is, if you look at this, it is discontinuous in the state variable because of this. There is also a minor problem with that. You should not have this R that becomes infinity, but this is standardly carried on with the maximum, carried on with the maximum principle. But this discontinuity makes it delicate to apply the standard ODE results. So what occurs here is that with a fine analysis of crossings of particle paths with this turning curve, which can be seen as particle switching, so a pedestrian that decides that he was moving forward and then he sees there are too many people there, the exit is clogged, I should go back to the other side, it is better. So this is the main feature we want to capture. And this crossing, this switching may only occur at particle exit times. So when a pedestrian leaves the corridor, the counting changes, and then another pedestrian decides, no, now there is one person less there, I will go there. And this permits somehow to reduce this strange ODE system to a stop and restart formulation as a sequence, a juxtaposition of at most n+1 classical solutions of well-posed ODE systems with continuous right-hand side. And therefore, you have well-posedness of this many particle fields. So now we know everything about discrete solutions, and somehow we have a nice discrete model which can be further discretized in time to do numerics. And we have compactness. Compactness of the turning curves. Bad button. It will take some time, sorry. Okay, so I was here. Compactness of the turning curve is simple if you use the linearity of C, linear costs. And it is much more complex actually if it is not. And at present with Theo Gerard, we are essentially fighting with these parts of the argument. How bad is the dependence of the turning curve of the solution for nonlinear costs? And here comes into play the kinetic formulation or fine information about the dissipation measure, while in the case of the linear C, all this is based on the weak formulation instead of the formulation. So somehow the story is that you renormalize with this cost, you renormalize the solution rho of the equation, and then you need to know the dissipation measure of the equation to write the sharp conservation of this renormalized quantity. So this for nonlinear costs is really a point that has to be better understood, and we are working towards. Now the compactness of rho n. What was established by carefully applying the previous works is that you would use the Wasserstein-Aubin lemma, which was put forward in Di Francesco Rosini works first, with respect to time, plus BV bounded space, following the Rossi-Savare abstract Wasserstein-Aubin lemma, if this BV bounded space were available. And then, unfortunately, looking for interaction potential functionals to control variation was not conclusive, even if it is rather clear from simulations that the BV bound should be there. And the other point is that anyway, even if you succeed, you change your model a little bit, and then you have again months and months of looking for another function. This is somehow the inconvenience of this BV bound technique within wavefront tracking correlated techniques. And so what we did is actually to go to local compactness arguments, but stop for a second. Imagine that this work and then convergence would use again the BV bound following the way paved by Di Francesco Fagioli Rosini work. And then we add on the top the adapted entropy inequality for the huge model of Deborah, Madori, El Khatib, and Rosini, and then you end up with convergence. Now, this is the theory, and the practice will be to use BV log compactness and also BV log convergence, because BV was used in both, in compactness and in convergence. Now, what we will base on is a one-sided Lipschitz regularity in space, which is a local property of entropy solutions of LWR because it is a strictly concave flux, and it gives you local compactness. It is compatible with finite volume approximation, including discontinuous flux color conservation laws, which was observed in a paper of Towers of 2018, and Abraham Silla sitting here used it quite a lot for many applications and graphic models to get compactness in complicated situations. Then, what is more important for our purpose is not that it is compatible with monotone numerical schemes, it is compatible with FTL approximation, and even Graziano-Stivaleta's thesis says us that it is probably the best way to see the entropy nature of the FTL scheme if you don't go to the Lagrangian version of Holden and Driscoll. If you stay with the Eulerian representation, what you directly see from the FTL scheme is exactly Olenek or Hoff inequality that increase the entropic nature of the solution. But now what I'm interested in is just the compactness, the DV log, not the compatibility with the entropy. And the point is that this argument actually supports localization, so you don't need your whole particle system, you can just have a part of the particle system, which you can complement if you wish with some fake particles which do not count for the final result. And in this way, with a simple covering argument, you find compactness away from the turning curve, which means that finally you get compactness almost everywhere because the turning curve is of codimension, is of full codimension, is of dimension 1 in a two-dimensional space. So it doesn't. So now we need to pass to the limit with DV log, which actually works the same as usual, I would say, with full DV. If you take test functions that are constant in space in the vicinity of the turning curve. And then because this kind of test functions is dense, you are finished. So this is the scheme of how you get the DV log and how you use the DV log to conclude to pass to the limit. So what comes from it? The main outcome is for sure existence for the Hughes model, even with the linear costs, but for general data, including the pedestrian switching situations that are treated here for the first time. Then one problematic thing, you will see why I say it is problematic, is that DV regularity of ρ by these arguments is only ensured locally away from this turning curve. But the good point is that we did it in a traffic compatible way. And we even produced a discrete Hughes model, which by the way can be used as a numerical tool. And then using this as a numerical tool, what we observe is that the dependence of the evacuation time on the cost parameter is or seems to be discontinuous. And apparently Max has a program of what should we do next about it. So this should be a beginning of some other stuff. Okay. Now, well, I'm essentially trying to understand mathematical structure of problems, and I'm happy when applications come, so I cannot say more about where we should head from here and what kind of optimization can be produced from here. And so I change the mathematical approach to the Hughes model now to try to understand this existence of solution in a less traffic compatible way, because if we already know that the model makes sense from the traffic perspective, then I just give me other mathematical tools to study. And the mathematical tool, which seems extremely natural for this kind of problems, is a fixed point formulation. Okay? So in the fixed point formulation, you just take the two ingredients of the problem and you consider that given psi, you define the map that provides you the solution rho, which is continuous flux LWR here. So here is setting the flux discontinuity. And then starting from Carlson Towers with a work almost finished of a PhD student of Denmark who collaborated also with Carlotta. And if you wish something which is much more robust and covers not only this case, but almost any case of any coupling in a one-dimensional LWR kind problem, then you can go to the general results obtained by Abraham-Silo very recently. So you have existence of this in different ways. Okay, and then B is the operator which gives you the interface psi knowing rho the density. Okay, and you make compositions of these operators, and if you want to use this viewpoint to existence, what you have is to choose functional spaces to apply some fixed point, and contractive fixed point is out of reach here, whatever be the time horizon t, but Schauder fixed point is okay if, so what Theo Girard did, if you take linear costs, because it gives you a much better properties of this operator for the reasons I mentioned above. You don't need a normalized formulation for C of rho, you just use the weak formulation for rho in order to understand the T dependence of psi. Then you take the W1 infinity topology for psi, which works for the linear costs, and we think it will not work more generally. The A1 topology for rho, which should be the main choice anyway. And then we use the weakest compactness framework of Panov, or essentially the same as Lyons-Bertam-Tadmor, if you don't assume low regularity, and we end up with existence. Okay? And for general costs, it's a work in progress. And what we would like to do by taking in the team Emmanuel Chassagne, who is a fine expert on Hamilton-Jacobi with discontinuous flux, we would like to go to the 2D flux model, which will combine the difficulties of hyperplotting discontinuous flux with difficulties of Hamilton-Jacobi with boundary conditions which are different on the walls and on the exits, and finally bring you again to something about discontinuous flux formulation. Now, what I would like to discuss is the uniqueness strategy. Because previously I worked on a couple of problems of similar kind with a moving interface involving the discontinuous flux. And the strategy that worked was a Gromov-like strategy, which provides locally Lipschitz and time and one dependence of rho on the initial datum if you have two ingredients which are of the following kind. So the ingredient A would be the estimate of the difference of rho two solutions at time capital T as function of initial difference plus a term which comes from the standard techniques of flux dependence for scalar conservation laws. You can use Boucher-Pertam or Carlson-Risebrough, or the framework, the most recent robust framework provided by the works of Colombo, Mercier, and several co-authors. And all this is essentially the same and can be adapted to discontinuous flux problem within. I mean, for the needs we have here, it's essentially the same. And we did it with Frédéric Laboutière, Nicolas Segan, and Takio Takahashi in a toy fluid particle interaction model. And then Paolo with Maria Laura de Limonache started to do it. They did this estimate for the problem they formulated of slow vehicle embedded in LWR, and it was finished. This problem was closed by changing the way the interface depends on the solution itself by making it a non-local problem, so more stable by Abraham-Silo. And the lesson we'll learn from this is that this gives you the restriction of BV regularity of rho. And here I have to remind you that we don't prove existence of globally BV solutions. So this is the first point where we don't like. Okay, but I think the discussion is open. This may not be totally bad way to proceed. The problem arises in the next step. It's like in this publicity for Schweppes. What would you expect from here? So what would you expect from here? I think that you would expect that now I give you an estimate of psi1 dot minus c2 dot in terms of this at time small t, and then I close this with Gromov, and it is done. And it doesn't work. It doesn't work because the operator B that defines psi from rho does not have this nice property. but it has a even nicer property, actually, extremely restrictive, much more restrictive. There exists some universal tau and k that such that on some time interval from 0 to tau, the whole integral here, the whole contribution of the integral is just bounded by the difference of the initial data. And because this tau is universal, you can bootstrap your estimate. At some point, you will find k to the power number of steps. You have to go to capital T, but this will give you the desired local Lipschitz estimate on this in terms of that. But what I didn't say to you is that both A and B, especially B, rely upon the restrictions that you have zero traces of the turning curve, which is essentially the assumption that the pedestrians will never change their mind. When they decided to go to one end of the corridor, they will continue going to this end. So actually, I'm reproving in a very general, similar general way, possibly generalizable to other situations. I'm reproving the uniqueness results that appear already in the paper of Deborah and Aspiliad, the situation where you don't have switch. So it's quite disappointing because it's a trivial case somehow without these dynamics you want to capture of switching. And this looks like bad news for the Gronels. To refine this a little bit, let me tell you that for A, I think it's just the laziness. I mean, once we see that for B, it was essentially necessary to suppose, then we suppose it for A and it worked rapidly. I think it can be bypassed for A, but for B, what you have to change actually is the way you compute size for growth. So if you make another model with more regular dependence, as you said, then you can hope for units. Okay. That's all about futures. Now I'll go to LWR with quick constraint on velocity and quick. So I briefly described the Colombo-Guatin model, which takes into account small obstacles on the road, and which on the top of the classical LWR puts a flux constraint, which is something which makes a rigorous sense because the flux is a quantity which is continuous across the interface and has at least a weak trace. Even if you don't think of the regularity of rho, it has a weak trace for just for Krushkov solutions. And then the Riemann solver is defined the following way. Please remember, because this will be my starting point for the conclusion. In the situation where you cannot have the classical situation, the classical Riemann solver of one constraint on WR, then you insert a non-classical shock, which means that you have a shock of acceleration, not a shock of braking, which is standard in the traffic context. And the questions I want to ask is, what would be the traffic assessment for this Riemann solver, even if it is very natural? But the main question, what would you do if you have a constraint on velocity instead of the constraint on the flux? And essentially, this is the question I want to ask. So the first point is, what was the original justification of a flux constraint? It was to take a thin constraint, so now your site is not a point, but what is in practice is something of 1 or 2 kilometers long on a very long road. So you put epsilon, then you insert a fundamental diagram with flux maximum, which is exactly at the level Q to which you want to limit the flux for this part of the road. And you find yourself with 2 discontinuous conservation laws, or rather conservation law with 2 discontinuities, with 2 interfaces. And then you want to pass to the limit. But what you do is that you admit a specific notion of solution for epsilon larger than 0. And this is easy to say this in 2021, where this is completely, we are used to it. But actually, the danger here, the fact that there are infinitely many equally consistent solvers, was a recent paper at that time by Mishra, Adimuti, and Galda. And what was used with by Rinaldo and Paolo was essentially the definition of solutions that goes back to John Tower's work and then many works of that time, of which I mentioned Segan Bovell. So lots of works at that time actually used vanishing viscosity approach. So if you look at existence proof in these papers, you understand that finally you are justifying traffic with hidden vanishing viscosity. This looks like bad news, but the good news is actually because of the geometry of the fluxes, it coincides with the optimal entropy solution in the terminology of signature, which is considered as the right notion for traffic because it leads you to flux maximization. So we did a very few on this, is that we take FTL-based justification, and now this epsilon thickening constraint problem we approximated with FTL scheme. The extension of FTL to its dependent velocity is straightforward. And this gives you a playground for numerical experiments with the goal to understand the Riemann solver. And we checked the above beliefs that flux maximization is a traffic compatible by doing this experiment. And now my point is, let's apply the blocks we prepared to velocity constraint problem where we take this instead of the flux constraint. So what we have from the previous study from Huge is that we have the local compactness properties. And towards convergence, I told to Massimiliano, okay, we just need stationary profiles and then L1 contraction, and then we are on the road and we can go very quickly. Okay, already stationary profiles for FTL is not easy because you don't have many particles, but this you can discuss. But what you cannot discuss is the lack of L1 contractivity. It is a fact, you don't have all the preservation. And so we have to go to adapted entropy inequalities in a long run. And I was supposed to conclude the computations before I give the talk, but I prefer to conclude the talk. So we strongly believe, very strongly believe it works. Now, in 4 minutes that remain, I will try to tell you something very deep. Justification within the formulas of interface coupling conditions. So to start with, I show you a problem posed in a half space, the left half space, which can be scalar conservation law, but you can also add here a viscosity. So capital F can depend on U and also on the gradient of U. And here you take your notion of solution, and on the boundary, you look at the trace of the flux and of the trace of U, which are t-dependent functions. And for every t locally, you prescribe some relation between the two. Now let me show you the classical relations, which are Neumann boundary condition, zero flux, Dirichlet boundary condition, yes, sorry, zero flux boundary condition, Robin boundary condition, and if you like, obstacle boundary conditions like this. If you look at it from far, you see that all these conditions say that the couple of trace of U and trace of the flux, trace of U here, trace of the flux here. So for Dirichlet, trace of U is given and trace of the flux is arbitrary. And for zero flux, the flux is given to 0 and the trace of U is arbitrary and so on. You find here a maximal monotone in all these situations. Okay? Monotone, you see what it means. Graph, because it is not necessarily a function, like you can see here. And maximal means you cannot add any single point to this without breaking monotonicity. Okay? And now, starting from Bardot-Leroux-Nedelec, it was implicit, totally implicit. Here, it was essentially explicit in Dubois-Le law, and we did it fully explicit with Kalimas-Guilly. When you take the hyperbolic situation and the formal boundary condition of this kind, it is projected, which is usual of singular limit problems. And you can think of boundary layer, if you think of any approximation procedure, it is projected to some different graph, which is a subgraph of F. Because in a scalar conservation law, U and F of U are related by a functional relation. In practice, if U has a trace, then the trace of the flux is F of this trace. So you have to project on the graph of this. Okay? And moreover, you can describe this beta tilde in terms of the Godunov numerical flux, which is a function of two variables, an explicit function, by saying that a couple belongs to this real graph if there exists a kind of virtual trace, such as the couple with a virtual trace and the same value of F is in beta, and you have this relation, which then leads you to a rather complete well-positiveness theory for boundary conditions given by maximum. And then I have to be very quick and say that you can do the same. I don't detail this transparency. You do the same for the interface problem, but just look here. You have two couples of traces, two couples of fluxes. So a couple of traces, couple of fluxes. So you have something which is in R2. And if you want to speak of maximum monotone graph of R2, you should precise the norm because it's not equivalent anymore, the different notions of Newtonism. And the one which is suitable for series based on L1 contraction is the one norm on R. And then you do exactly the same. You just imagine you want to mimic the procedure, you do the same. And then there is a very simple Kirchhoff test which will give you the basic vanishing viscosity solutions. And there is something different, what is called Kedem-Kachast, that we now explore with Giuseppe Copetti and Carlotta Donadello. And the use of it is here. This is Sept. You put the formal interface coupling condition, which will contain some simple modeling assumptions that are nature. And then you take the projection, and this brings you to the notion of solution through the interface Riemann solver, or through the interface Godunov of flux, or through admissibility germ in the sense of the theory we developed with Kenneth Carlson and Niels Rieser. And so my last point, I just go to the conclusion. Here, I put maximal monotone graphs that correspond to the idea I would do of the physics of non-classical shocks in constrained models. What I put here is exactly the definition of Colombo Guattari Riemann solver. It's the same logic as in the definition of the Riemann solver. And when I take the projection, I find the Aloshkin solution. This is totally expected. And here is what corresponds to the velocity formulation. And the only point here is that you have a choice here between rho L and rho R. And constructing Riemann solvers, Max came with the idea that rho L was stable. And by checking monotonicity of this, we came to the idea that with this choice, we have a maximum monotone graph and not with a different choice. And so then you compute straightforwardly the projected graph. And what you find is that for the velocity constraint, it boils down to flux limitation at some precise level you can compute from the intersection of couple. And so the conclusion is that the velocity constraint actually boils down to some precise flux constraint. And while this problem looks singular, this one is mathematically well posed, and so we are happy with this. Thank you for your attention.
Questions? Please in the question.
Well, thank you for this very broad presentation. All what you said is related to scalar observations. Do you have any insight about convex bounds on the vector flow into these two equations, or the case of two populations in traffic?
No. I would like to know more. Actually, all this stuff mixes, I would say, two ingredients that are quite happy to meet. The one about some formalism that permits to better describe the traces that appear, the relation between traces and fluxes, and the other one, which is the L1 contraction. The L1 contraction takes these traces, this formalism, and makes it work towards uniqueness, towards convergence proof, and so on. And so if you abandon L1 contraction, you still have some experience that comes from this. And I would be interested in exploring this, what we can do of it if you abandon L1. But clearly you can do less things. And the question is, what can you do? For instance, this recipe of projection, you could use it for systems. But I don't know to which extent, okay, in some situations it should work. We started a little bit with RRZ, but RZ or Raskol chunk is a very particular system. The second field is almost passive in this situation. It's driven by an equation which admits a renormalized formulation, which permits to some extent to see it as a decoupled problem of scalar conservation law and the transport equation. We are trying with Abraham to exploit this viewpoint to produce some kind of discontinuous flux division of IRZ. But to be honest, it is totally based on seeing first equation as scalar conservation law with some discontinuous flux. It's more or less like triangular system. And second equation is almost basic because it is a constant. So for this system, I think we can go several steps ahead. For general systems, I really don't. I know that Massimiliano with Andreianov-Chiarello and Luis started to study valves in the context of P system, and the questions that arise there are quite close to what we discussed with FTL approximation, which is not relevant, but as a Scott Kaplan questions.
Thank you. More questions?
Thank you for your talk. And curiosity, so you mentioned the extension to the 2D fixed model. What would be the boundary conditions in that case? Would we have in mind some special geometry of the domain?
Okay, for the traffic part of it, we will have exits, and I didn't say explicitly, but what we use is open-end condition, which boils down in the configuration in the directions we have. It boils down to zero directly condition. You formally prescribe zero directly, which means that persons evacuate free. And on the walls, I would take zero flux. But then for the Hamilton-Jacobi part, the question is more complicated because apparently the theory is delicate if you have discontinuities at the corner points. So when you have the exit that encounters the wall, it is not so clear what you should do if you take the pure Hamilton, first term. Then if you regularize, it becomes more clear. But essentially, I'm not in for the time being. We just formed a team which go from my side, the goal will be to have a concrete example of multi-D discontinuous flux hyperbolic problem. So I see Hamilton-Jacobi as the slave equation, but my colleague is the constant. So I don't know.
More questions? Online. Okay, so we can then comment for the next. And So we can pass to the next talk, or next speaker is Chiarello from Untitled Chapter.
Thank you. First of all, I would like to thank the organizers for this kind invitation. I'm Andreianov-Chiarello. I work at Polytechnic di Torino, and today I talk about the statistical mechanics approach to macroscopic limits of cut following traffic dynamics. In particular, I will present a joint work with Benedetto Piccoli and Andrea Costin. So I will start with a short introduction about traffic models. After that, I will talk about genetic derivation of cut following traffic dynamics, and I will perform a numerical test at the end. So. Okay. There are, as you know, probably there are different approaches to model traffic flow phenomena. In particular, macroscopic models that are based on the description of collective behavior of vehicles, that are based on PDEs, and that they describe high densities, and that are suitable to describe large networks. After that, there are microscopic models that are based on the description of individual vehicles and their interactions. They use audience systems, and they are suitable to describe low and high densities. And there are mesoscopic models that are more or less the link between microscopic and macroscopic models, and that are based on gas kinetic equations and stochastic interactions. So the framework of this talk will be the mesoscopic approach. In particular, we will start from macroscopic traffic models, and we will recover well-known macroscopic models. In particular, we will use gas kinetic, the gas kinetic theories. We will imagine interactions between vehicles, like collisions between particles in gas dynamics. Okay, these are some microscopic models, well-known microscopic models. For example, the first one is follow the leader dynamics. We can see that the acceleration here of vehicles is proportional to the relative speed between the leading vehicle and the rear vehicle, and over the distance between the rear vehicle and the leading vehicle. After that, there is the optimal velocity dynamics. Here you see this capital V, that is a desired speed that depends on the difference between the position of the leading vehicle and the rear vehicle. And what we will analyze in this talk is this general curve following model that is a composition between the follow the leader one and the optimal velocity one, so this one, and we will start from this, and we will recover the macroscopic correspondent model. So this is just an illustration of the situation. So we have the leading vehicle here in J+1 and the rear vehicle here in X3. So we start with the kinetic derivation of following traffic dynamics. And okay, let us consider this sufficiently large ensemble of indistinguishable vehicles. So we have this discrete in time stochastic particle model that we can write directly from our microscopic model. Here, theta and C are independent binary random variables. Here, theta is Bernoulli of delta t, and C is Bernoulli of epsilon delta t. This means that follow the leader. Here you see that this is the follow the leader part, and this is the optimal velocity part. So follow the leader interactions are more frequent with respect to optimal velocity interactions. So in this setting, so this is the probability of follow the leader interactions is proportional to delta t, and the probability of optimal velocity interactions is proportional to epsilon delta t. So optimal velocity updates happen at much lower frequency than follow the leader speed updates, because this epsilon is much lower than 1. Rho denotes the traffic density in the neighborhood of the point st. The function h models the head weight of the vehicle. Lambda is the density, the sensitivity of the driver in xt, and a is a relaxation rate. So now we would like to give an aggregate description of our particle systems. And in order to do this, we use this kinetic description. Here you see that the right-hand side of this equation is a collisional-Faulkner operator. In particular, this T is a collision kernel that elevates the position of the rear vehicle and the leading vehicle. We can choose this collision kernel. In particular, if we choose the collision kernel equals the delta in x minus x, we have the classical Boltzmann type of description. If we choose the collision of the kernel, the collision kernel like this, we get the envelope type kinetic description. We prefer the envelope type kinetic description because traffic models derived from a Boltzmann type kinetic description cannot reproduce backward wave propagation, because the interacting vehicles in this case are assumed to occupy the same space. Here you have that the leading vehicle and the rear vehicle occupy different positions. And okay, here B prime and B second are defined like this. So there are follow the leader interactions and optimal velocity relaxation interactions. Okay. Now we can, choosing the collision kernel like before, we can rewrite the equation like this, and we obtain the envelope type kinetic description that we desire. So we can observe that here the rear vehicle is in x, the leading vehicle is in x plus h of O. In order to make computations more amenable, we approximate this distribution function, the distribution function computed in x plus h, like this. Okay, and we define these terms with this collision operator. Here you have the classical Boltzmann term here, Q, and here you have the envelope correction that comes from this term. Here just the relaxation term. Okay, so now what we would like to do is to pass from the microscopic scale to the macroscopic scale, and we perform the hyperbolic scaling like this. So we scale the time and space like this, and we can write this equation. Now we perform the hydrodynamic limit. So epsilon as epsilon tends to 0, we can split this equation into two equations. The local equilibrium of follow the leader interactions, this one, and the transport of the local equilibrium, this equation. Okay, we can rewrite the local equilibrium in evolutionary form, passing on the quick time scale, and we can rewrite it like this. So now the aim is to recover the equilibrium, so the local Maxwellian from the first equation, and to put the local Maxwellian into this equation in order to get our macroscopic model. So this is the equation of local interactions in a weak form. Here, V prime is described the follow the leader interactions. So defining the density like this and the mean velocity like this, and choosing the test function phi equals 1 and equals v, we can notice that the density is conserved by local interactions, and the mean velocity is conserved by local interactions. This means that our local equilibrium is parameterized by these macroscopic quantities, so rho and v and u, sorry. And so we can write the local Maxwellian like this, and we can prove that this is unique, computing the total energy and its variance. Now we can we can put the local Maxwellian in the transport of the local equilibrium, and we obtain something like this. Substituting the collisional invariance into this equation, we get exactly this system. If we define this traffic pressure like this, the system that we obtain is exactly the inhomogeneous or absolute traffic. So we started from a microscopic model composed by follow the leader part and an optimal velocity relaxation part, and we get as a result at the macroscopic level the inhomogeneous RZ. So we can study the linear stability of this system at the macroscopic scale. A uniform traffic flow corresponds to a constant density and mean speed. So we can consider a related perturbation like this one, where eta is a small parameter, and we can write the linearized system. We can choose the perturbation like this, and we can put it into the linearized system, obtaining this not very nice computations, but at the end we can say that the stability is obtained if the real part of this omega is less than or equal to 0. So the stability condition that we get is this one that involve the sensitivity parameter of the follow the leader interactions. This condition does not involve the relaxation rate A, so the relaxation rate of the optimal velocity part. The superposition of follow the leader and optimal velocity Microsoft dynamics under the assumption that the latter are less frequent than the former produces a macroscopic flow whose stability is ruled by the follow the leader driver sensitivity. And this is consistent. This stability condition is consistent with that one derived in this paper. For a generic inhomogeneous RZ. Just in order to compare, if we consider just the microscopic band of optimal velocity model, we get this stability condition that involves the relaxation rate A. So, if we consider now the same distance in time stochastic particle model, but here we consider theta and c Bernoulli random variables of delta t. So if we consider that follow the linear interactions are frequent as the optimal velocity interactions, we can repeat the same argument, so we can write the kinetic equation in this strong form. We can recover the local Maxwellian after transforming the hydrodynamic limit. We can plug the local Maxwellian with the transport equation, and at the end, we obtain the LWR, the classical LWR. Okay. So in this case, the LWR model will be formally viewed as the limit of our second order system in the relaxation dominated regimes as A tends to B. And the high relaxation rate is the macroscopic counterpart of an optimal velocity frequency comparable with the follow the leader frequency at the particle level. So now we start with the numerical test, and so we consider this initial density and this initial velocity mean speed. Okay, and we can see that as epsilon is decreasing, we get that the particle, the numerical test of the particle model matches the macroscopic solution. So you can see here the match of the two solutions, and the same happens for the LWR, so considering theta Bernoulli delta T over epsilon and C Bernoulli delta T over epsilon. Here you can see some oscillations, but this is quite normal if you consider simulations of particle models, in particular where the solution is discontinuous. So here there is a shock, so this is quite common. And okay, just a few words about the stability of the homogeneous model. This is the stability condition for particular choice of the velocity and okay, lambda and h. We consider this initial condition. So this is a constant, density and velocity perturbed by this term. And you can see here that for different values of the relaxation rate A, we get different profiles. This is the unstable regime. You can see that perturbations are amplified, and you obtain stop and go waves here because okay, this is the RZ model. And you can see that in the stable regime, everything works fine, and perturbations are decreasing exponentially in time. So I think that that's all. Thank you for your attention, and these are some references.
Are there questions in question? Online? So I think that we can thank again Lisa for the nice talk.